So I wish you all the best, right? So you know, you need to know how to learn this subject using with my style, all right? So it might be different from what you have done before with other professors, but this is my way, so you need to follow my way, okay? Right, so today we go to chapter 5, single phase systems. What is single phase? We are talking about solid, liquid, and gas, right? So in this chapter 4, we already learned input equal to output, and we know how to do the mass balance. So when you read the text, the information is all provided or is given in the problem statements. I'm sure you are familiar with this flow chart because this was in your final midterm exam paper, right? Okay. So as you know that we give you all the nouns, and you need to write down all the unknowns in the flow chart. And then this is what we are going. And according to the statement, you know how to do this. In chapter 5, we want to remove some of these unknowns, and we provide you more information regarding the specification. For example, like single pass conversion. This is the things. But in chapter 5, we want to determine various physical properties. You know, in order to find out the equations, you know, in order to do DOF, you have numbers of unknowns, right? And you need to find equations. So there are four directions for you to find out equations, right? The first direction is what? How many species? It can be molecular species. It can be atomic species, right? This first direction. The second direction is called specification. Specification is that here is a single pass conversion. It's something to do with, for example, the numbers unknown here and unknown here, right? So this is what we create the equations. So how about the third one? The third one is called physical properties or physical laws. For example, density, vapor pressure, etc., etc. So something dealing with the properties, the physical properties. So you need to find out the density, or you need to know how to do this. Okay, physical properties. What's the fourth direction? Physical constraints, right? Physical constraints like x plus y plus z equal to 1, which is not difficult at all. So the main thing you need to think of in order to create equations are the equations where you can find through these four directions. Okay? So this is the example, is determine the variables like physical properties. For example, you have a flow chart like this, you have numbers of unknown, you have independent chemical reactions, right? You have independent molecular species and other equations. So this is one of the directions to get an equation, right? Another three are specification, physical laws, or we call physical properties, or physical constraints, right? These are the three directions you need to find. You need to get the equations. And chapter 5, in this chapter, we are going to provide you some of this information, and you need to find out. You need to know how to do it. So these variables using physical laws, such as what? Such as density. You know, density is easy. But if I want to tell you that the mixture of water and ethanol at 20 Celsius, please find out the density of this mixture. So what can you do? Measure it or check the book to find out, right? So these are the directions. In chapter 5, we are going to tell you how to do this, how to find out the density of a mixture, liquid or mixture gas. And vapor pressure. For example, the vapor pressure of water at 20 Celsius, or the vapor pressure of water at 70 Celsius. or the vapor pressure of the water plus alcohol at 70 Celsius. Okay, so can you get the answer, or how can you get the answer? Okay, vapor pressure. And solubility, like sodium chloride in water. What's the solubility of sodium chloride in water? Okay, at 20 Celsius, for example. And heat capacities. Okay, so these are the variables we want to show. We want to let you know how to get the answer. And chapter 5 is only single phase. So we are only talking about solid, liquid, or gas. We don't talk about solid, liquid, or liquid gas phase. This will be two phases, and we will introduce this topic in chapter 6. So how to determine, let's make it the easiest way, which is how to determine density. How to determine density. So determination density, there are a few directions, a few methods. First is look it up. You find out the density of the mixture of the water and alcohol 50-50 at 20 Celsius. You probably can find the density of this mixture in Paris Chemical Engineer's Handbook. Okay, this is the first one. Or when I was young, when I was a student, I go to the library to check chemical abstracts. There are hundreds of books of the chemical abstracts, and you need to find out the information you want. But now, like you, it's 30 years ago I did it my way, but now, as you are the student, you don't need to go to get this handbook, you don't need to go to library to find out the answers in the chemical abstracts. You just use your hand and type. That might be easy. That's easy, okay? Very easy. So the first one is, if you can have information and you can get it from a book, that's good, right? Let me block this first. Oh my God. I'll talk to TA then. Right. Okay, so let me take a picture of this. Okay, and the second direction is estimate it. What does that mean, estimate? Estimate is that, you know, as I just told you, if a mixture of the water and alcohol, and we want to find out the density, and with a portion of 50-50 or 40-60 or 30-70, you can have thousands and thousands of the combination. So you can make a chart, make a plot, and make a chart, or you do the simple calculation to estimate. So this is second direction. The third direction, of course, that's more straightforward. You use equipment, or you measure the density. Okay. So in the case of there's no literature available, or when the property must be known with a precision greater than that provided by general estimation formulas. Okay? So this chapter, we're only dealing with density. Easy, very easy. Okay? Density of gas, density of liquid, or density of solid. So, you know, when we do the mass balance, it's input equal to output. So we are dealing with the mass or moles. And of course, we give you volumetric flow rate or volume. So you need to convert volume or volumetric flow rate to mass or mass flow rate or mole or molar flow rate. What you need, the conversion factor is what? It's density. That's why this density is important. That's why that's what we call physical laws or physical properties. Okay, so the section 5.1, we are going to dealing with the density of the solid and liquid, which is easy. The section 5.2, the density of ideal gas. And section 5.3 is density of non-ideal gas. Okay, and section 5.3 and 5.4 is the important one. You need to know how to dealing with the density of the non-ideal gas. But today we only introduce you 5.1 and 5.2 only. Okay, so the section 5.1 liquid and solid density is, the density will be changed because the temperature changed or the pressure changed. Right? So the density versus temperature. So if temperature increase, the density will, we are talking about liquid and solid. So if the temperature increase, that means what? Generally, value of the material of a liquid or solid increase. If we increase the value, that means what? The density will decrease. Right? Right? That's easy. How about pressure? If we increase the change in the pressure does not cause significant changes in liquid or solid densities. These substances are therefore called incompressible. So when you think we cannot change the density of the ice, we cannot change the density of the water, but we can change the density of vapor, right? Steam. Okay, because the different three phases in terms of H2O, you can the density of the ice and density of water cannot be changed. Okay, so section 5.1 we are only dealing with the temperature. So find out the density of liquid and solid. How can we find out the density of liquid? Three directions, right? Three methods. First, look it up, different temperature, because we are not talking about pressure now, and measure it. So we can find out in a textbook B.1 and in appendix B, pure substance. Okay, you can find out the temperature density in Paris Chemical Engineers Handbook. Okay. And third method is estimate. No data available, mixture of the liquid, right? So there are two methods. First is called by pure component mass fraction value additivity. Additivity means what? You add up the value. For example, you have 50 milliliter water, you have 50 milliliter alcohol, and you put it together. Will value of this mixture become 100? If the answer is yes, this is what we can use. It's called value additivity. Okay. So this is an example. So you have, because for example, V1 represent water, V2 represent alcohol. So V1 will be mass times X1. X1 is a fraction of water, right? Divided by density of water. And then V2 will be equal to M, the mass, times X2. X2 is the fraction of the alcohol divided by what? Divided by density of the alcohol. The M is the total mass together with water together with alcohol, for example. Okay, so if V1 can plus V2 become the total volume, so if you put these two together, so you become like this. So as a result, you know that if you move the M from the right to the left, you can have this equation, V1 plus V2 divided by M equal to what? This is what? This is volume, right? And divided by mass. So this is a rho over bar. Rho over bar means what? Average density, right? 1 divided by rho over bar. And this one, X1 divided by rho 1 plus X2 divided by rho 2 here. So as you can see, this is how you find out the density of the mixture with the fraction. Fraction A and fraction B. So, but if you have 2 components, 3 components, 4 components, this you can use these general terms, right? 1 divided by rho over bar equal to summation from I represents species from 1 to n, right? So it's xi divided by rho I. Okay? So xi is the mass fraction of the species. Okay, 1, 2, 3, 4. And rho I will be the density of the species. Okay? Right. So this is equation 5.1-1 in your textbook. And the reason we use this equation is because the value can be added. We call value additivity. Okay? But another thing is that by the pure component densities, you might say, well, Professor, sometimes I don't do it in this way. I use weighting. This is a more common way to do it. What does that mean, weighting? You have a fraction of the density. And because you have a fraction of the mass, or mass fraction, so you can use something like this. So rho over bar equal to the summation I from 1 to n xi times rho I. Xi is the mass fraction. So this is what normally we use. But which one is better? This is equation 5.1-2. Which one is better? 5.1-1 or 5.1-2? It depends. Okay, one of these estimation formulas might work better for some species, and another might work better for another species. So it depends, right? For example, if you have a mixture of the H2SO4 plus, with the water, 5.1-2 is better. But if you use the mixture of the CH3OH to water, what is this? Ethanol, right? And then if you use the 5.1-1, this is better to represent the density. Is any rules we can follow? Yes, it's only one simple rule. Which method should you use? Okay, for the value additivity, the liquid species with the similar molecular structures. So if you have a similar molecular structure, you use value additivity, which is the equation 5.1-1. Okay, for example, all straight chains hydrocarbons of near equal molecular weight, such as N-pentane, N-hexane, and hexane. And for these three species, you can use value additivity. Well, you don't really need to remember this. Okay, I just give you an example only, because it really depends. And for the fraction of the density, there's no general rules to follow. So don't worry about this. Okay, so this is the example to show you how to determine a solution density. For example, this is a 50% H2SO4 and plus 50% H2O at 20 Celsius. And the example wants you to find out the mixture density of the mixture using CGS system, the gram per cubic meter. Okay? So the first thing you need to find out the density of the H2SO4 and the density of the H2O at 20 Celsius. Okay? So for if you check the Paris Chemical Engineer handbooks, there's already somebody gave you the answer, which is 1.3951 grams per cubic meter. This is the answer you found. You get this answer from the book. However, if you use two different equations, you can get two different answers. First one is you find out the density of the water at 20 Celsius, and you from the book, from the Paris Chemical Engineer's handbook, and also as well as you find out the H2SO4 at 18 Celsius. You cannot find exact 20, okay? But so you use 1.834 grams per cubic meter. So if you use the equation of the 5.1-1 and you put the numbers, the 50-50, right? You put the numbers and density here. As a result, you got a density. The answer is 1.29 gram per cubic meter. So this is the answer using value activity method. How about average density? The fraction of the density. Again, you find out the density, the density of a pure component, a pure species, and you apply the 5.1-2 equation here, and you get the density is 1.42 gram per cubic meter. Okay. So comparison of these three methods. First, look at the Paris Chemical Engineering book, Chemical Engineer's Handbook. Density is 1.39, and use equation number 1, density is 1.29. Equation number 2, density is 1.42. Which one is closer to this? Because handbook is tell you the answer which is close to the true value, right? True value. So this is more true. So 1.42 is better, right, compared to 1.29. Okay. Easy, right? Easy. Right. So now let's. In order to find out the density of liquid and solid, it's very easy. Okay. So now let's take a look of the ideal gases. What's the ideal gases? So if you have three phases, this is solid, right? Solid means what? The atoms pack or molecules pack very closely, and the density is very high. This is solid. And when you go to liquid, that means that the distance between all the species has a little bit loose, away from each other. Okay, this is liquid. In terms of gas phase, they are all the species are very far away to each other. This is gas phase, right? So the ideal gases is what? The density of the solid or liquid doesn't change a lot while temperature and the pressure change. That's for sure. Although the temperature increase, the density decrease for solid and liquid, but it doesn't change much, because as you can see, the distance between all the atoms are not too far away. So the density of this and density of this doesn't change much if the temperature changed. However, if we increase the temperature to make the species vaporize from liquid to gas, the density will change a lot. The density of gases follow the pressure, volume, and temperature relations. So you know that density will be changed because of pressure change. Density will change because of volume change. Density will change because of temperature change. And as you know that, you have learned this in your high school. So, you know, for the Boyle's law, you understand if we have a constant numbers of the molecules and the temperature is a constant, and if I change the volume and I will see something change with pressure. So this is called Boyle's law. That means what? The volume inversely proportional to pressure. So volume inversely means what? If volume increase, the pressure will decrease, because volume times pressure will equal to a constant. This is called Boyle's law, right? You learned this in high school. Okay, the Charles law, what's Charles law? Charles law is that the volume directly proportional to the temperature. That means what? Volume increase, temperature increase, because volume divided by temperature will be equal to a constant. Let's say this is a K prime. Okay, this is called Charles law. Okay, so if we make the moles and volume as a constant, and we change the pressure and the temperature, we realize the pressure directly proportional to temperature. That means what? Pressure divided by temperature equal to another constant. Pressure increase, temperature increase. Pressure decrease, temperature decrease. This is called Hamilton's law. Okay, in the end, Avogadro's law is that keep the temperature and pressure constant. We find out that the value directly proportional to numbers of the moles. So V divided by N equal to another constant. So as we put this all together, Boyle's law, Charles' law, Avogadro's law, and these are all constant, right? So when we put this all together, we realize P times V divided by N, N times T is equal to another constant. So this is what we call ideal gas equation of state. Okay, and as you know, this is Mendeleev in 1874. He said PV equal to nRT. I'm sure you know this very well. You learned this in your high school. Okay, this is called ideal gas equation of state. So what is equation of state? What is equation of state? Equation of state is the relationship between the molar quantity N and the volume and the temperature and pressure. If you put these 4 parameters together to become an equation, this equation will be called equation of state. Okay, equation of state. So now you know equation of state. And do you know the ideal equation of state? If we put these 4 things together and become a constant, that will be called ideal gas equation of state, which is made by Mendeleev. PV equal to nRT. Okay? Ideal gas equation of state. So when is this applied? Because it's ideal, so you might know, you might have a non-ideal equation of state. But in what case you can use ideal equation of state? Normally, you need to, if you want to use this equation, normally is high temperature and low pressure. High temperature means what? High temperature means that it's more than 273.15 K, which is 0 Celsius, above 0 Celsius. Why you need high temperature? Because high temperature means that the species is more gas-like, right? Because the high temperature means from, if you think of the H2O, low temperature means become liquid and solid. If you increase the temperature higher, it becomes gas, right? So if it becomes gas, you will become ideal gas. So that means you want to use high temperature, which is 273.15 Kelvin. And low pressure. Low pressure means what? Low pressure means inside this, you have only not a lot of the molecules. If you have more, the distance between each other will become less, right? Then you will become, you tend to become what? Liquid or solid. So that means less pressure means less molecules in this system. So in order to apply ideal gas equation of state, you need to think of 2 conditions. First, high temperature, which is more than 273.15 Kelvin. Second, low pressure, which is what? Less than 1 atm, 1 atmosphere. Okay? In this case, ideal gas equation of state is okay for most of the gases. Okay? So if the temperature is low, too low, the pressure too high, what does that mean? Temperature too low, it becomes solid, become liquid or solid. So you cannot apply ideal equation of state. If the pressure too high, it becomes liquid or solid. Okay? So please remember these 2, 0 Celsius and 1 atm. So let's go to the 5.2a, the ideal gas equation of state. So the ideal gas equation of state can be derived from the kinetic theory of the gases by assuming what? Theoretically, why this can be regarded as a gas, ideal gas, is that because gas molecules has a negligible volume. That means what? This is one atom or one molecule, and we don't count the volume in this space. So gas molecules has a negligible volume. The first condition. The second is exert no forces on each another. That means what? These two has no interaction, no forces, no attraction, no repulsion. Okay, there's no forces between each other. But this is not real, right? That's why it's called ideal. Because all the materials has a volume. All the materials has attraction or repulsion forces, right? The third one is collide electrically with the walls of their containers. So if the material hit the wall, it's electrically, there's no energy exchange. Collide electrically means what? There's no energy exchange. So if the speed come in to this way, the speed will, the same as this speed will come out from this way. So there's no energy exchange between the wall and the molecule. Okay, so if you apply to these three, then we can regard this system as an ideal gas system. Then ideal gas equation can be applied. So this is PV equal to nRT. But if the V divided by T in this case and N divided by T in this case, we can use this instead. P over dot equal to N over dot RT. What does that mean? V over dot means what? V over dot means volumetric flow rate, right? N over dot means what? Molar flow rate. So when we talk about this, we are talking about a process. A process. So please remember this P is absolute pressure of a gas. V or V over dot is a value of volumetric flow rate. Right? N or N over dot is the numbers of the moles or molar flow rate. R is a gas constant, and T is the absolute temperature of the gases. I'm sure you learned this when you are in high school, right? No problem at all. So expression of the ideal gas equation, for this one, the equation can be expressed as what? Because in this case, you might say, well, Professor, when we talk about density, where is the density? There's no density in this term. So where is the physical law here? That's what we are going to show you now. So if you move the n from right hand side to left hand side in this equation, V will become what? V over caret. What is this? V over caret means what? This is called specific volume. Specific molar volume. Because regardless of how many moles, so this is one single mole, the value of one single mole. Okay, so PV over caret equal to N equal to RT. Please remember this equation because you need to know the meaning of this V over caret. V over caret means what? V divided by N. Or V over dot divided by N over dot. Because it removes the terms of the time here, right? Right. So V over dot, N over dot is called specific molar volumetric flow rate. Okay? So a gas whose PVT behavior is well presented by the PV equal to nRT equation is said to behave as an ideal gas or a perfect gas. So now the problem is R. Where can you get R? It depends on different unit, right? It can be CGS, molecular engineering system. It can be CGS system. It can be SI system. And you can find out this. You can find out this constant by internet or from the book. So, and another topic is that how can we find out errors in estimate volumes? Let me find out whether we have. Okay. The epsilon is that errors in estimate value. So once you find out some numbers, you need to know this system is ideal system, and can we use ideal gas equation of state to represent all the parameters or not? So expressed as a epsilon equal to x ideal minus x true divided by x true times 100%. What is x? X can be P, T, pressure, temperature, mole, or volume. So if the epsilon, absolute epsilon value is less than 1%, that means that this is ideal gas. For example, if you put the pressure ideal minus pressure true divided by pressure true, and times 100%, if epsilon is less than 1%, then that means this system is an ideal gas system. Or you can put the temperature here, or you can put the volume here, right? So ideal gas behavior is that if the ideal volume, or if the V, especially for the volume, if the V over carat ideal is PT divided by RT divided by P, right? So if it is 5 liter per mole for the diatomic gases, that will be ideal gas. If the V over carat ideal is more than 20 liters per mole, that's for the case of another species. Okay? And in this case, epsilon absolute value of epsilon will be less than 1, maybe expected. So volume, if you find out a specific volume is more than 5 liter, so epsilon generally is less than 1% for the pressure, temperature, whatever. Okay, this is called ideal gas behavior. Right. So I think I will stop here today because I have something to do tonight.